Hello, this is Dr. Benjamin Norris from the Chemistry Department at Frostburg State University. Today we're going to talk about electrophiles and nucleophiles. The structure on the upper right is hydroxyacetone, a molecule that contains both an electrophile and a nucleophile in its structure. We're going to learn about how electrophiles and nucleophiles are common participants in organic chemistry reactions. Once you learn to recognize electrophiles and nucleophiles, you'll be able to much more easily interpret the reaction mechanism or propose mechanisms for new reactions, both of which are important skills in organic chemistry. Recognizing nucleophiles and electrophiles combined with understanding arrow-pushing mechanisms, which will be the topic of an upcoming video, are really fundamental to helping make sense of the large number of reaction mechanisms that you will study in organic chemistry. Most organic chemistry reactions have polar reaction mechanisms. That means that they have two electron mechanisms. All of the bond breaking and bond forming that's going on involves the action of two electrons at a time. These reactions or mechanisms are also called ionic mechanisms because they frequently involve ions, or heterolytic mechanisms because when bonds form or break, both electrons end up coming from the same place or going to the same place. Heterolytic two-electron mechanisms are represented by arrows that have two hooks, the same kind of arrow we've been using for proton transfer arrows and resonance arrows. And there's an example of a mechanism step in a polar reaction mechanism shown where the bromide anion is forming a new bond with a carbocation. We'll learn in an upcoming video how to interpret that particular information, but right now this is a representation of a polar two-electron mechanism step. The other major class of mechanism step in organic chemistry consists of the radical mechanisms, which are one-electron mechanisms. So all of the bond forming, bond breaking happens one electron at a time. They're also called homolytic mechanisms because when a bond breaks, the two electrons in that bond go their separate ways. One goes with one atom, the other goes with the other. When bonds form, each atom coming together to form a bond brings one of its electrons to the bond forming party. And there's an example of a homolytic mechanism shown at the bottom of the slide. And you can see that we're using different kinds of arrows to represent homolytic mechanisms. Radical mechanisms or homolytic mechanisms only involve one electron at a time, so the arrows only have one hook on them. These look a little bit more like fish hooks if you've ever been fishing, and we often call them fish hook arrows. But basically the number of hooks on the head of the arrow is an indication of the number of electrons being transferred by that are moving and what that arrow is representing. So one electron, one hook, two electrons, two hooks. In your introduction to organic chemistry at the undergraduate level, the vast majority of all reactions you will study are two-electron reactions, and the vast majority of arrows you should be drawing are two-electron arrows. Generally, the types of radical reactions that are commonly studied at the undergraduate level are confined to one or two chapters total out of a textbook. So radical mechanisms are not as common, and you should not be drawing radical one-electron fishhook arrows as your default type of arrow. If you're going to default to a type of arrow, default to the two-electron arrow. Here is a depiction of that same two-electron mechanism step from the previous slide, except now I've drawn in all the lone pairs on the bromide anion. All polar reactions in organic chemistry consist of interactions between an electrophile and a nucleophile. The electrophile is a thing that loves electrons, so our carbocation is electron poor. If you count up the electrons on that central carbon atom, it only has 6 electrons, not the usual 8 for the octet. So this is a species that wants more electrons than it has. And therefore it can accept an electron pair to form a new bond. We already have a definition for something that accepts electron pairs to form new bonds, and that is a Lewis acid. In general, the terms electrophile and Lewis acid are pretty interchangeable, with some, fine technicalities that Lewis acidity is describing a thermodynamic phenomenon and electrophile is describing a kinetic phenomenon, but generally something that's in a Lewis acid is an electrophile and vice versa. The bromide anion is acting as a nucleophile. Nucleophiles are things that love the nucleus. They have more electrons than they know what to do with. So the bromide anion has 4 electron pairs, and they're able to donate a pair of electrons to form a new bond, and that's what the mechanism arrow on this slide is showing: the bromide anion taking one of its pairs of electrons and forming a new bond. Things that donate electron pairs to form bonds are Lewis bases, and so again, the overlap between Lewis bases and nucleophiles is pretty straightforward. Everything that's a Lewis base is a nucleophile, and vice versa. The reason why we make the distinction that the acid-base behavior is thermodynamic and the nucleophile electrophile behavior is kinetic is because some things are good bases but poor nucleophiles, and vice versa. There's some things that are really, really good nucleophiles that are very, very weak bases. And the same thing goes with the acid electrophile thing. So while the same structural features make something an electrophile and a Lewis acid, it's not a one-to-one correlation between acid strength and electrophilicity. We'll talk about these relationships more when we talk about substitution reactions in specific in an upcoming topic. There are several types of electrophiles that are common in organic chemistry. One, like the example in the previous slide, are species that have less than an octet of electrons around one of the atoms. And so here is our reaction of bromide anion and the carbocation again. This carbocation and its central carbon only has 6 electrons. It's an electrophile. Note that this situation does not require that central atom has a positive charge. Here is an example where our electrophile is the boron atom. It only has 3 bonds, and so it has less than an octet. But because of boron's valence, 3 bonds for boron is a neutral molecule. Electrophiles can also be things that have polarized sigma bonds. So any species that has a carbon bond to something more electronegative is polarized towards that more electronegative atom, and that carbon becomes an electrophile because the more electronegative atom, through induction, is pulling away some electron density at that carbon atom. And here is an example of a reaction involving a sigma bond electrophile. The carbon-bromine bond is polarized towards bromine, and the most common cases are, when carbon is bonded to a halogen like fluorine, chlorine, bromine, and iodine, or when carbon is bonded to oxygen and nitrogen containing leaving groups. And again, we'll talk about what leaving groups are when we start to learn about substitution reactions. And the third type of common electrophile are polarized pi bonds. So here is an example of a reaction involving an electrophile where the electrophile is a pi bond. The carbon-oxygen double bond is polarized towards oxygen, so the carbon has a partial positive charge there as well. But unlike the previous case where it was a carbon-bromine single bond breaking, it's the pi bond that is breaking in this case, and the carbon-oxygen sigma bond is hanging out. Polarized pi bond electrophiles are common when you have a carbon that's double bonded to or triple bonded to a more electronegative atom like oxygen or nitrogen. Some carbon-carbon bonds are also capable of being polarized electrophiles if one of those carbon atoms has an electron withdrawing group on it. Specific examples of that won't be covered until late in organic chemistry 2. Just like there are 3 types of electrophiles, there are 3 common types of nucleophiles. One of them that's most easy to recognize are the lone pair nucleophiles. Like the bromide anion in this reaction mechanism, lone pair nucleophiles are things that have lone pairs that can be used to form new bonds. There are also pi bond nucleophiles. The electrons in a pi bond can be used to form a new sigma bond. And sigma bonds are generally stronger than pi bonds, so there's some thermodynamics incentive to do this. So here is an example where the pi electrons in the alkene are being used to form a new sigma bond to the boron. All types of pi bonds are capable of being nucleophiles. Carbon-carbon, carbon-oxygen, carbon-nitrogen, double bonds, and carbon-nitrogen triple bonds. The bonds between carbon and more electronegative atoms are nucleophilic at the more electronegative atom. Carbon-carbon pi bonds can sometimes display a preference for which side they're nucleophilic at, and that's a topic that we will cover when we get to the addition reactions of alkenes. There are also sigma bond nucleophiles, where the electron pair that is being used to form a new bond comes from a sigma bond between two elements. Here is an example where the boron-hydrogen bond is being used as a nucleophile. The electron pair in the boron-hydrogen bond is being used to form a new bond to carbon. The most common situation that leads to sigma bond nucleophiles are bonds between hydrogen or carbon and less electronegative elements. And I'm using the generic M because most of these elements are metals, though a handful are metalloids. The most common situations you will encounter in your introduction to organic chemistry are boron, magnesium, lithium, and aluminum. But chemists around the world have discovered dozens of these reactions using all kinds of metals, including zinc, silicon, tin, palladium, ruthenium, rhodium, etc. In our next video, we will be practicing identifying electrophiles and nucleophiles. Thank you for watching.